What is going on, everybody? Welcome back to what I believe is the last example videos for systems of ODEs, and what I believe the last video for me in terms of differential equations. After this, I'll be going to partial differential equations that some of you may or may not be interested in or have to take, but this is going to be the last example video, and it is just one example, probably going to be a long one, but we'll just go ahead and jump right through it. And so this one is just as any other ODE or system of ODE. It's just pretty much solving this system of ODE. And if you remember countless times, as I've been saying, the first steps in solving such ODE or system of ODE is to always put this in a matrix, or just put it in matrix form. So we're going to have x prime, y prime is going to be equal to 7, 4, negative 5, 3 multiplied by x and y. And then now we're going to take this matrix and find the eigenvalues. And so remember, we take the determinant, or subtracted by take the determinant of this minus lambda times I, set that equal to 0, and so we will essentially get 7 minus lambda, 4, negative 5, 3 minus lambda. And so this is going to be equal to 7 minus lambda times 3 minus lambda plus 20 is equal to 0, or lambda squared, that is really lambda squared, minus 10, 20, 41, plus 4, minus 10 lambda, plus 41 is equal to 0. So I don't know how to factor out a 41, and so we are going to go ahead and use the quadratic formula. Yeah. So the quadratic formula is lambda is equal to negative b, so 10, plus or minus the square root of b squared, 100, minus 4 times ac times 1 times 41, all over 2a, and a is just 1, so it's divided by 2, and so this is going to be equal to 5 plus or minus 1/2 times the square root of 100 minus 164, or 5 plus or minus 100 minus 164 is negative 64. The square root of negative 64 is 8i, so, and then 8i divided by 2 is 4i, so this is going to be equal to 5 plus or minus 4 times I. And so this is our eigenvalues. We have 2 because of the plus or minus, and we also see that 1, it is a complex eigenvalue, and 2, it's a complex conjugate pair. So this is really good because all we have to do is just focus on one of them, one of the eigenvalues, find the corresponding eigenvector, find a solution, and you find a solution for both. That's amazing. So I am going to pick one. I don't know which one it is. But I guess I'll go with the negative. So now we are having our eigenvalue, and I'm going to pick the conjugate. So lambda is going to be 5 minus 4i. And so we'll get the matrix 7 minus 5 is 2, 4. So 2 plus 4i, 4 negative 5, and then this would just be negative 2 minus, no, because of the minus, plus 4i. And so the corresponding eigenvector, well, this is going to be a little bit tricky. Cancel out the 2 and 4, 2, 10, 2, 5. So the first one's going to be 5, So that's going to give us 10 plus 20. And so the other one's going to be 2 plus 4i. And that is going to be our eigenvector. And just for like sanity check, we will have 5 times 2 plus 4i is equal to 10 plus 20i. And then negative 5 times 2 plus 4i is equal to negative 10. That's terrible 10. Negative 10 minus 20i. When you add those together, that gives you 0. Yeah, and then just for like ultra sanity check, 5 times 4 is equal to 20. And then 2 plus 4i multiplied by negative 2 plus 4i, we will get negative 4 plus 8i minus 8i, and then 4i times 4i is negative 16 minus 16, so this will be negative 20, and those two will cancel out. So this eigenvector is a valid vector. So now we are going to continue with the process. And so right here, you will do the usual. So everything else is like pretty much the same as like how you've been doing. So we will have the solution to being x of t is equal to v, I guess v bar, e to the lambda bar t, or 2 plus 4i, or I guess 5, 2 plus 4i, e times 5 minus 4i times t. And that is our solution. But we don't like imaginary numbers because they can be pretty tedious. But we can reduce this or make this more, I wouldn't say realistic, but more into the domain of real numbers. And so what this becomes is the eigenvector so far stays the same. And then we are going to expand this using Euler's formula. So this becomes e to the 5t all multiplied by cosine negative 4t plus I times sine to the negative 4t. We are now going to multiply all of this and hope that we don't do some algebraic error. And this is going to be so much fun. So let's go ahead and get to it. So we are going to not multiply the e to the 5t. The e to the 5t will say e to the 5t. So this would be equal to e to the 5t multiplied by the eigenvector and the cosine and sine. And this will give us 5 cosine to the negative 4t plus 5i sine. Well, actually, I'm going to do this. I 5 sine negative 4t. And in the bottom part, this is going to be 2 cosine negative 4t plus I times 2 sine negative 4t plus I 4 cosine negative 4t minus 4 sine negative 4t. And this is a lot. So let's just hope I did this right. So now what we're going to do is we're going to combine like terms and separate them. So we're going to get e to the 5t. The reals are at the ends, so let me put these together. So 2 cosine negative 4t minus 4 sine negative 4t plus I times 2 sine negative 4t plus 4 cosine negative 4t, and then here we'll have 5 cosine negative 4t plus I times 5 sine negative 4t. Cool. Cool? Cool. And so now what do we do? So, you remember in that little proof that I had at the very end, little overview is you found your solution. So now we're going to find the imaginary parts and the real parts and make them their solutions. And so essentially what ends up being is our solution becomes xt is going to be equal to c1 e to the 5t multiplied by, let me actually use the color, 2 cosine negative 4t minus 4 sine negative 4t and 5 cosine negative 4t plus c2 e to the 5t multiplied by the imaginary one, which is 5 sine negative 4t, that's not going to be centered, 2 sine negative 4t plus 4 cosine negative 4t. And so that will be our answer. And so our, not particular solution, but like our individual solutions, x1 and x2, is going to be equal to, well, this part is going to be x1, and then this part is going to be x2. So what we get is 5 e to the 5t multiplied by c1 cosine to the negative 4t plus c2 sine to negative 4t. And in x2, we can factor out the 5, or e to the 5t. So e to the 5t, and then multiplied by c1, 2, so c1, 2 cosine negative 4t minus 4 sine negative 4t plus c2, 2 sine negative 4t plus 4 cosine negative 4t. And like another way you can write this is e to the 5t multiplied by 2c1 plus 4c2 cosine negative 4t plus 2c2 minus 4c1 sine to the negative 4t. And so these will be our solutions, and this will be the answer to this problem. Now, a quick little disclaimer: if you use the lambda, or the lambda instead of the lambda bar, the answer will be slightly different. It should still give you the same thing. The only thing that's changing are the signs, but that will also be a valid solution. And so when it comes to checking your work with someone else, it becomes difficult to see if your answer is right. And if y'all have different answers, it is possible that both of your answers are correct, because there's like many ways to write, or there are many solutions to certain systems of ODEs. It doesn't necessarily have to be a particular solution, especially when it comes with eigenvectors. as they have like the general vector and then the ordinary ordinary eigenvector, or the ordinary vector and the general vector. And when you saw those, you saw that there's different solutions or different ways to get the same thing. And so that is like a quick little heads up. If I believe, yeah, like I mentioned, if you do the lambda is equal to 5 plus 4i, again, you'll get a different answer, but it will look relatively the same. It's just the signs are going to be off. And then, not to mention, if you play around with your trig, with like the cosine of -4t and the sine of -4t, you can do something with the negative, or like the -4, and again, that will change the answer as well. So yeah, that is it for this video. That is it for this example, and I'm pretty sure that this is it for me in terms of differential equations. So moving forward, I'll be focusing on partial differential equations, kind of, sort of, well, for the most part, because to be honest, PDEs, to solve them, you break them into ODEs. So that's just a little teaser. And so I'll be seeing some of you guys there. And so as of now, goodbye.